Let's start with the last talk for today. I'll present Jaume de Dios. He will talk about the hotspots conjecture. He will tell us why it's false.
So thank you very much for letting me speak. So this was a talk that originally was supposed to be given by Mitchell Taylor, who's one of the two people who's in the paper. So, I mean, he couldn't make it, but still here in spirit, and also with Alex Su, who's a grad student at the University of Washington. So I'm going to talk about a question that's been a bit of an emotional roller coaster for everyone involved. So Stefan's like nodding in the back. So it's basically about a lot of very reasonable statements that turn out to be false, and a couple of very unreasonable statements that turn out to be true. So let's start with the reasonable statements as follows. So we start with a piece of material, some sort of potato, which is insulated from the environment, has a uniform material but a non-uniform temperature distribution. How does the heat in the material evolve? Well, we know this. It satisfies the heat equation. That's the line on top. And what does thermally insulating mean? It means that we don't exchange any heat with the environment. The heat goes from cold to hot places, so it goes in the direction of the gradient of the temperature. If I'm not exchanging any heat with the environment, what that means is that the gradient cannot cross the boundary, because otherwise I would be exchanging heat through this boundary. So this is the heat equation of an insulating material. And when we simulate it, basically what happens is what we expect. The temperature of an object left alone will become more uniform. The temperature will go from the hotter areas to the colder areas until we basically reach the average temperature. And this matches our physical intuition of the world and matches the simulation, so we like it. But then we ask, we get greedy and we ask, can we say more? Can we say things about how we reach this average temperature? Like, for example, which points get there faster, which points get there slower? And we zoom into the microscopic temperature fluctuations. How do we do that? So instead of plotting basically the temperature, we plot the difference between the temperature and the average temperature, because we expect the temperature to go to the average temperature, and we divide that by the maximum of this so that we get some meaningful object. And we basically copy the same simulation as before, but now by looking at the simulations. We get something very different, but we somehow still converge to something, and it's something that has the coldest and the hottest points, so the points that microscopically deviate the most from this average temperature, right at the top and right at the bottom. And you can run a lot of variations of this simulation with a lot of random generic domains, and you get very similar pictures. And one pattern that you see is that the hottest and the coldest point on the material are at opposite places of your of the object, and sort of as far as they could be from the bulk of the object. And this makes a lot of sense, because somehow the material has to be, a point in the material has to be able to see all of the material, and that takes time. And if you're far away from the bulk, it's going to take you longer to see the bulk. And which points are the furthest from the bulk? The ones at the boundary. So when we look at this, what we see is that for large time, the largest fluctuations, the hottest and coldest point, are at the boundary. And this goes through simulations. This goes through a bit of through common sense as well. And maybe it's even true. How do we study these things? Well, we go back to separation of variables. Whenever we want to solve an equation of this kind, what we do is we write our initial data as a linear combination of eigenfunctions of the Laplace operator. So here we have a bunch of Laplace eigenfunctions, and we write our function as a combination of them. What do we know about them? The first one is 1. The constant 1, Laplace of 1 is 0. That's an eigenfunction, just a 0 eigenvalue eigenfunction. And the normal derivative is also 0, because it's 0 everywhere. And then we have a bunch of them, which have to be orthogonal to the first one, because eigenfunctions are orthogonal. And in particular, they have mean 0. And I can write my initial data as a combination of those. Not only that, I know how to solve the ODE for each term on the sum. When I have an eigenfunction, the PDE becomes an ODE. Just the time derivative is proportional to the Laplacian, which is proportional to yourself, up to an eigenvalue, so you just get a decay according to the eigenvalues. So then if I want to solve for one guy, I first individually solve, which is just multiplied by an exponential. I add all of the contributions, and I get the total sum. Not only that, but I can learn about what's happening in the, how do you call it? In the asymptotic fluctuations. What's going to happen in the asymptotic fluctuations? I'm summing a bunch of things which exponentially decay in terms. The exponentially decaying term depends on the eigenvalue. So there's things that go to 0 faster than others. Which one's the one that's going to remain at infinity? The one that goes to 0 the slowest. So out of all coefficients in this eigenbasis expansion, I look at the first coefficient that's not 0. And this is the only one that's going to survive at infinity. It's the one that's going to dominate at infinity. So now we understand more of the asymptotics at infinity. And we can also prove that the average goes to the average. Why? Because the first term is going to be constant and it's going to be the average. The other ones have mean 0 and they're going to go to 0. So asymptotically I go to the average. Now, let's try to see what we can say about the fluctuations. So we expect that the largest fluctuations are in the boundary. And we know that asymptotically we go to one eigenfunction. How do we merge these two intuitions? Well, for every Laplace eigenfunction, knowing a Laplace eigenfunction, the maximum and the minimum should be at the boundary. That's like what happens if we mix everything that we believe to be true at this point. Yeah. Not only this is not true, this is not true for easy reasons. Like if instead to go like to fancy domains, we just go to the ball, we have a symmetry problem. We see that for the ball, the first eigenfunction, the third eigenfunction is radially symmetric. In particular, it can't have the maximum and the minimum at the boundary because it's constant at the boundary. So it can't have both extreme at the boundary. But this is the third one. Generically, when I have like a generic initial condition, the first coefficient will be non-zero. So maybe it's like our intuition works except like with probability 0. Like generically, the first eigenfunction will be alive. You will converge to the first eigenfunction. So maybe this is all a story about the first eigenfunction. In this case, we have like a split, like a repeated eigenspace. So first and second are the same. But maybe this is a story about like for the first eigenfunction, the maximum and the minimum is at the boundary, which would imply that for generic initial data, the maximum and the minimum of the evolution of the heat equation goes to the boundary, which meets our intuition, and we're very happy. Or that's what Jeffrey Rauch thought in 1974, and he conjectured this. He said that for nice enough domains, where nice is left to your interpretation, and that's what it talks about, the maximum of the first eigenfunction should be at the boundary. So why is the first one special? If we go to the Rayleigh-Ritz quotient, this first eigenfunction minimizes amongst all mean zero functions the ratio between the Dirichlet energy and the L2 norm. So it's trying to make, it's a function that has mean zero, that is big, but has the gradient as small as possible. This also explains why you want the maximum at the boundary. What you're doing is you're picking up the longest direction of your domain, and you're slowly going from positive to negative. That's at least what happens for most reasonable domains, and there's a bunch of conjectures in like convex geometry and so on that could be summarized with the eigenfunction sees the longest direction and goes from negative to positive because it's trying to change as slowly as possible. Okay, so this is our conjecture, this is our game for today. What do we know about it? Okay, so we know how to solve it over the reals. This is easy. I mean, we want a bounded domain for it to make sense. The problem's dilation and translation invariant. So in the reals, like R1, there's only one possibility, one interval. We can solve it exactly. The first eigenfunction is a cosine. Goes from 1 to -1. Maximum is at the boundary. We win. Well, maybe R2 is equally easy. Well, no. But we know some things. After a lot of work, turns out we can prove it for triangles. This is extremely difficult. Like this doesn't have the right to be as difficult as it is. Like nothing reasonable works, but you can prove it with a lot of effort for triangles. Basically, what makes triangles hard is that like, they don't necessarily have like a preferred direction. If you look at a long and thin triangle, you win. But sometimes you have domains that have a special direction, and then you can use it for something. Like for example, if you have a convex set that's like somehow like with an axis of symmetry, then you use it as a special direction, and you use the special direction, and you show that you grow from one direction to the other in this special direction, and you win. Similarly, there's these things which are like called Lip domains, which are domains between one Lipschitz functions. They have a long direction. If you have a domain that's somehow bounded between like one Lipschitz functions, it's going to be longer than it is taller. So you have the long direction, and you expect the eigenfunction to be monotonic in this long direction. Once you know how to pick a direction, essentially you're done. In RD, the situation is a lot more complicated, and this 2 should be a D. We know how to do it for cylinders or for products because the eigenfunctions tensorize. And we know how to do a generalization of this case, where there's like you're long in particular ways in certain directions. Okay, so this is the positive situation. Now, what do we believe? So it depends on how optimistic we are. If you're extremely optimistic, and I think Rauch was extremely optimistic, you would believe that it holds for any smooth enough domain. And this was sort of like not clear for 25 years until Burzi and Werner came up with that example over there. So the way to think about that example, let me play it. So what's happening in that example is that we're disconnecting. It's like a circle, but we've disconnected the inside of the circle from the outside of the circle. What that does, if we remember that we're trying to minimize the Dirichlet energy, the efficient way of doing it now is to be in constant on one part, constant on the other, and it's extremely cheap to go from one to the other. If you want to think it from a heat equation, basically the heat cannot go from one part to the other. And basically now you've managed to make the radial solution, like this third eigenfunction that was a problem, you've managed to bring it down to the first one by creating these very disconnected domains. So at this point, you're like, okay, maybe holes are the problem, because like we know a bunch of examples, but they're all about like joining things with tubes in complicated ways. But maybe it's a topological problem. And you could think about domains without holes, like topologically simple domains. In dimension 3 and higher, we know that this doesn't help. Like topology is trivial because of an analytic capacity argument. Like topology is completely irrelevant. But in dimension 2, topology is very important. And this is basically, I want to say, one of the biggest, if not one, the biggest open case. Like what happens if you're 2 dimensions, you don't have holes, you suddenly get access to complex analysis, maybe the conjecture is true. The other one is maybe convexity. So, you know, convexity is a very strong way of saying you don't have holes. You don't have holes, you don't have cavities, it's as good as it gets. And this was believed to be the case. This was believed to be the most reasonable version of the conjecture for a very long time. But this turns out to be false. It turns out to be false in high dimensions. We are not sure after which dimension. Like the proof is a limiting argument around d equals to infinity. But we know that this is false. But at least let's hope that for 2-dimensional convex domains it's true, right? That's where we are. We're like not in a very optimistic situation. We don't know what's true. We know a lot of, like some things are true, some things are false. And we don't know how to proceed. And then Steinerberger comes and he gives us an alternative. He says, okay, we know it's sometimes false. Let's try to measure how false it is. So he defines the hotspots ratio, which is the maximum between the eigenfunction inside and the eigenfunction at the boundary. If the conjecture was true, this would be 1. But maybe we can see like which is the worst domain or things like that, or how false it is in a certain dimension. And we can ask ourselves, like, what is the worst, how bad can this be, right? Like, I mean, it's still like, we can't like violate our intuition by a lot. And we know that we can violate it a bit. But Steinerberger shows us that we can only violate it by at most a factor of 60 in any dimension. I think that's like kind of like the biggest shift. Like you realize that the conjecture doesn't get worse as the dimension goes to infinity. It's uniformly bad in every dimension. So there's some game to be played. And then Mariano, Panzo, and Wang came a little bit later and showed that the conjecture is actually quite true. Like, they uniformly bounded by 5.5, and they asymptotically find the square root of it. Square root of it is like 1.6. Like, it's, you know, it's not really that bad. And it's like, for every domain in every large enough dimension. And that's when, like, Mitchell, Alex, and I came in, and we're like, okay, there's these people trying from above. Let's try from below and see if we can meet in the middle. And as we were trying that, we actually managed to find what is the exact value of this constant. So we have this weird PD, and we can show that the value at 0 of the solution to this weird PD is the maximum of this hotspot constant. First thing, let me show you what like SD looks like. It's 3.2 in dimension 3, goes down to square root of phi. So Mariano, Panzo, and Wang, without knowing, had actually guessed the right asymptotic. And now let me tell you what this is a solution of. Let's go back to the circle. This is the 3 eigenfunctions that we know the circle has. Sort of the claim is that by microscopically modifying the circle at very, very small scales, I can add yet another eigenfunction on the circle, which is radial, and it's below the other ones. This is a bit of a crime because it's not orthogonal to the first one. It looks pretty positive. I mean, if you look at the PDE above, it's an elliptic PDE with positive coefficients starting at 1. It's going to be bigger than 1, so it's not orthogonal to the first one. But my claim is that I can build something that sort of looks like this by pushing the negative parts to the boundary. And of course, the Laplace, the eigenvalue has to be at most the eigenvalue of the first one because it has to be below. And if I need it to be at most the eigenvalue of the first one, I get the PDE above. So basically, the claim is that I can somehow inject a fake eigenfunction, and not only that I can inject a fake eigenfunction, but that doing so is sharp. Let's start with the sharp part. This is an embarrassingly,
Yeah, just to make sure I don't with you still. So this is so the way to compute this hotspot ratio for the circle. So you're only talking about the circle in this case.
So the hotspot ratio for just the circle is 1.
Oh, yeah.
Because the first eigenfunction has the ratio at the boundary. But my claim is that I can microscopically modify the circle to inject something else that looks like this, and then has a very large hotspot ratio. The circle itself, and that's kind of like why this is very unreasonable. The circle is not an extremizer. But my claim is that I can microscopically perturb the circle to produce something that's very close to it, but is an extremizer. Yeah, the circle itself, the hotspot ratio is 1. And that's kind of, that's why everything's so wrong about this result. Like I'm telling you that like the worst case is extremely close to the best case. Like everything is extremely discontinuous. And like that's basically why it's a whole, like everything's wrong sort of about the result. So let's start with the upper bound. And the upper bound is also going to show us why things are unreasonable. So we want to bound this. I've normalized my eigenfunction so that its maximum value at the boundary is 1. And then it solves this PDE. And I want to bound this. How do we bound this? Well, we apply maximum principle. The maximum at the boundary is 1. Elliptic PDEs, if I make the boundary bigger, they get bigger inside. This is a terrible idea. We have an eigenfunction. It should be positive some places, negative some places. I'm just lifting it to be 1. This should not give you a sharp proof. Like this is Stefan's idea, but like this, like when he implemented it, like there was no reason to think that this would be a sharp thing to do. So we just change it, and we change it to be 1 at the boundary. Now there's this really cool inequality called Talenti's rearrangement inequality that tells us that whenever I have an elliptic PDE of this type, I can rearrange the right-hand side. So I can apply symmetric rearrangement to the solution, or I can apply symmetric rearrangement to the right-hand side of the equation. And it turns out that applying symmetric rearrangement to the right-hand side is always bigger. So it's better to rearrange the PDE than to rearrange the solution. So in this case, it tells me that if I modify my PDE and I symmetrically rearrange it to make it in the circle, I'm going to get a bigger function in the sense that it's when I rearrange the original one, it's going to be below this new guy. And this is almost the form that I originally wanted. The only difference is that I have the eigenvalue of omega instead of the eigenvalue of the ball. But we have the Jaeger-Weinberger inequality, which tells me that the eigenvalue for the ball is bigger than the eigenvalue for any other set of the same area. So I can just get this and substitute this one for the one on the ball. Every step of this should not be sharp. They're all sharp. That's kind of like the wrong thing about this. It's an extremely simple argument which happens to be sharp. How do we see that this argument is sharp? We go back to Burzi and Werner. So, I mean, their example had like 3 or 4 spokes, depending, they consider both in different papers. But we can make 5. We can make whatever number we want. We have this 4-parameter family of domains. What does it depend on? The 2 radii, the number of holes, and this angle. And, we can think very hard, or we can use a computer and try a bunch of them. So here I'm adding more lines. Here I'm changing theta. You can imagine doing thousands of these computations. But before we do that, just with these ones, we'll already get most of the story. Basically, there's 2 cases. Depending on the parameters, you get a radially symmetric situation and you're in game. Or you get basically the same situation as the circle, where it's anti-symmetric and the hotspot constant is 1. So either it looks like Werner or it looks like the circle. If we want to find the counterexample, we have to optimize over the situations that look like Burzi-Werner. And we do that. And when we run thousands of examples, we see that the extremizers look like this. What are the take-home messages of this? The first one is that good examples have a lot of holes. This is also good from mathematics perspective, because understanding an example with 3 holes is extremely difficult, but understanding an example with infinitely many holes is extremely easy because it homogenizes and it becomes radially symmetric. So there's this whole theory of something called the Neumann sieve that's been used for also similar problems by Hofmann, Ostenhoff, and Nadirashvili before, that tells you that you can like take limits and make it radially symmetric. So the math is done. The second thing that we see is that the radii go to 1 and that the thickness goes to 0 at a precise rate. And then when you go to the literature, there's a bunch of literature on this thing called the Neumann sieve, and you manage to take the limits. And what do you get in the limit? Well, you see that you need that the eigenfunction, that the eigenvalue has to be at most the eigenvalue of the ball. Why is that? That's because of the competition. Like when the eigenvalue is more than that of the ball, we are in the radial situation. As soon as it goes above the one on the ball, it would be energetically favorable to just switch to the non-radial situation, and then the hotspots constant would be 0. So you need to tune rho 1, rho 2, and theta, which you can do, so the eigenvalue of this like ghost eigenfunction is like right below the optimal one. And you send the radii to 1 and everyone at the boundaries, because then when you homogenize, when you send everyone to infinity, you satisfy the Laplace equation, and you're radially symmetric. So you end up with someone that satisfies exactly the same PD as before, and you've slowly sent the negative part to the boundary until it's disappeared. So if you just fine-tune everything carefully, you recover the sharp result. So yeah, that's basically it. It was very surprising, like for us, like on both sides. First, we were trying, like this project started because we were numerically trying, like what can we get? And then when we tried numerically what we could get, we saw that like the extremizers were they satisfied the hypothesis of the type of proofs that Stefan was doing. We're like, wait, Stefan's like approach of like substituting the value for the maximum is actually what's happening at the eigenfunction. And then once you know that, you just go back, you start pulling everything, and magically it works. So yeah, we were very happy. It was a very surprising project because of, like things worked. Like with a result that we very much didn't expect. Thank you very much.